Hello and welcome to Module 25, which is Weathering and Soil Science. So pretty much soils are pretty important for when we talk about environmental science because it pretty much determines the type of environment that will be available for organisms and the amount of energy that will be available because ultimately all energy, unless it's a photosynthesizing organism, comes from the sun or plants. So we're going to talk a little bit about how soil is formed and look at a soil profile. So soil is formed when rock is weathered. So it goes through a process of weathering and erosion. So there's two types of weathering. There's physical and chemical. So physical, it just breaks down into smaller pieces, whereas chemical, it's actually breaking chemical bonds. So the rock might be dissolving or something along those lines. So just think of physical as smaller pieces, whereas chemical is actually changing it into something else. And so we've got chemical weathering is by mainly acid precipitation, so acid rain. And so what happens here is there's a high content of sulfuric acid, so sulfur dioxide in the atmosphere. And then that combines with the water, and when it rains, it becomes slightly more acidic. So to us, we wouldn't be able to tell that it's acid rain, but to organisms that rely on water through their roots or through their skin, like amphibians, then it definitely does affect them. And we'll talk more about that later when we talk about pollution. But that's chemical weathering occurs mainly because of the acidity of rain. Right. So if we look at this weathering, this is physical. So here we've got a rock on the left, and that rock is undergoing maybe freezing. So there's water that gets into the cracks. It freezes, water expands when it freezes and causes the cracks to get bigger. Or maybe potentially we have a tree root. You can see on the right. So the tree wedges its roots within the cracks of the rock, and that causes it to spread out. But either way, it's just because of physical weathering. So the rock is only being broken down into smaller pieces. It's not chemically changing. It's just getting smaller. And then we've got erosion. So erosion's occurring as well. And so erosion is just the removal of rock from one place to another. So there's two processes that occur with that. We've got wind, water, ice move downhill, or organisms. So you've got natural, they're both natural, but we've got basically water. So wind, water, ice. Wind would be blowing the rock around. Water is moving it like with a river. Or a hillside or something. And then ice, as a glacier moves downhill, it carries sediment. And then living organisms, so they're burrowing, making holes underground, burrows, and moving the soil around as they do that. All right, so soil in environmental science, it serves a lot of different functions. So it's a medium for plant growth, it filters water, it's a habitat for creatures that live underground, and it also filters pollutants. So there's a lot of different things that soil does besides just growing plants. All right, so if we look at these things, these are the ecosystem services. So the services that a soil provides is growth, so kind of what we talked about in the last slide. But those would be ecosystem services, and that's really important to know. Anytime we talk about anything in this class, it's important to know what the ecosystem service is. So what does this thing that we're talking about provide? So for soil, it provides plant growth, filters water, organisms live in it, and then it also breaks down nutrients and filters as well. All right, so the way soil forms is we start with the parent rock, which is usually the bedrock. And so that would be our immature soil on the left, and that's this picture. And so we've got different weathering processes occurring. We've got physical and chemical weathering. And so that starts to break down. You can see at the surface. It starts to break down the rock, and then you mix it with organic material. So you've got this organic material growing, and then as that dies, it mixes in and supplies some nutrients. And then physical and chemical weathering are still occurring. So you get the breakdown of smaller and smaller pieces of rock mixed with organic material is basically what soil is. So you can see over time, it's a well-developed soil profile. So a soil profile is just different layers, which we'll talk about in a minute. So this would be our immature soil. And in Redding, we have a lot of immature soil. So California is fairly new geologically speaking compared to the rest of the U.S. And so we've got fairly immature soil. If you look at, if you've ever dug anywhere here in Redding, you get to the parent material pretty quickly. And what's on top is a clay layer. So we don't have usually a lot of soil unless you're near the river or something like that. And then you get to young soil. So some places, maybe along the river, there's young soil. And then mature soil, this would be in well-established areas. So the Midwest is a really good example of mature soil. So that's how soil forms. And this is over thousands and thousands of years. So it takes over 1,000 years to form 1 inch of soil. So soil is pretty important and something that we need to make sure we conserve. All right, so I talked about the formation, but parent material is just that rock beneath. So it's referred to a lot of times as the bedrock. There's a huge variety. So here in the West, we have a lot of granite. So our soil will come from granite. All right. So the parent material is, it depends on where it's at. So the climate, of course, if you've got a tropical climate versus a desert, that's definitely going to make a difference on how that parent material weathers. Topography, same thing. So we've got mountains versus flat area, rivers versus mountaintops. So that's going to make a big difference on how it's formed as well. And then organisms. So organisms digging up through the soil, organisms maybe like plant material mixing with the soil and making it nutrient rich. And of course, time. So all of these things, these four things, really play a big factor in the development of soil. And then soil degradation is the loss of it. So this could occur in a variety of reasons. We had a big soil degradation event, and that was the Dust Bowl. So that was a combination of drought and poor farming practices. But natural occurrences could be, potentially like the Carr Fire, for example. So losing a lot of organic material can definitely affect the soil for a short period of time. If we have a flooding event, something along those lines. So that could cause soil degradation or just overuse. So using too much nutrients, over farming, stuff like that. All right. So we're going to talk about the horizons. And so the horizons are different layers of soil. So there's, and there, it varies where you're at. So some places have really well developed horizons. Some places don't. And so here, since our soil is fairly young, we don't have a well-developed horizon down by the river because of the flooding of the Sacramento River and the nutrients and things that the water brings. There's a well-developed horizon, so we'll look at that. We'll go outside this week and we will look at the soil horizon of the front lawn. All right, so here's the different horizons. So we've got the O horizon, which is the organic material up on top. Then you've got the A horizon, which is the next layer down. This is usually your topsoil. And then E horizon, this is where you have alluvium. And so you have nutrients being passed through from the surface to the layers below. In Redding, we tend to have B and C. Depending on where you live, if you're by the river, you may have this, but really we have very little of this top here, the O, A, and E. We have a lot of B and C there. So B is accumulation of nutrients, metals. It's often clay. And then the C horizon is subsoil also. So you can see there's a coloring difference, and you'll see that when we take a soil profile from outside. And so you'll see there's a difference in color is usually how we can tell the material. And so this is the closest, C is closest to the bedrock. So bedrock would be down below, and we would not be taking a sample of bedrock because that's usually solid rock. But these are our layers, so just have them memorized. But O horizon, organic, just think of organic. And then they go in order, except for the E, which is a leaching of metals. It's the alluvium horizon. And so it starts with an E. But otherwise, they go in alphabetical order.
Soil is essential. You walk on grass rooted in soil and eat food grown in soil. Plants and trees need it to grow, but what is soil composed of? Welcome to Moo Moo Math and Science and Soil. If you look at a chart of soil, you'll see that it is made up of 45% minerals, 5% organic matter like decaying plants and animals, 25% water, and 25% air. You can also study soil by looking at its profile and the soil horizon. A vertical layer of soil that shows all of the different layers is the soil profile. Much like your profile on Facebook, it tells others all about you. The profile of the soil tells all about the soil. A soil horizon is each individual layer of the profile. Each layer has different physical properties. The horizon layers are O, A, E, B, C, R. Let's take a look at what each layer is made up of. The O layer, or horizon, is also called the litter. It's composed and contains dead leaves, twigs, sticks, fallen trees. The O horizon is thin in some soils, thick in others, and not present at all in some types. The A horizon is also called the topsoil. It contains rich organic matter, along with some minerals. This layer contains decomposers. The decomposers perform the task of breaking down plants and animals. The remains of these plants and animals create a mixture called humus, which is dark organic material that forms in soil when plant and animal matter decays. E is also called the alluviated layer. As water moves down the soil, substances are removed and pulled out in this layer, resulting in a concentration of sand and silt particles. This layer may be missing in some soils. Horizon B is called the subsoil. It's lighter in color, many times it's reddish or brown in color, because it has less humus. It is a zone of accumulation where materials like clay collects from the movement of water downward. C horizon is the parent material. This layer contains much of the material that the soil was originally made from. It will contain rock fragments. Weathering breaks down the parent rock into smaller and smaller pieces of rock, and this layer is most often light in color. And then horizon R is the bedrock, a massive rock such as granite, basalt, or quartzite, limestone, or sandstone that forms the parent material for some soil. If you'd like to know more about soil, this playlist will help. And as always, thanks for watching, and Moo Moo Math uploads a new math and science video every day.
All right, so there are 3 properties of soil, physical, chemical, and biological. So we'll talk about those. So the physical properties refer to size and weight. So when we're talking about different particles, like the lab that you guys are doing, it's sand, silt, and clay. So those are the 3 types of texture that you guys are looking at, and that's what you're doing with the graduated cylinder, is determining how much sand, silt, and clay you have. And then permeability, you guys use the filter to do that. So how permeable is it? How fast does water move through it? And that depends on the texture. So clay, it's not going to move very fast. Sand, it'll move very fast. And then here's our soil properties. So we've got sand, silt, and clay. These are the 3 physical properties that we're looking at. And so we're determining, using this triangle, the amounts of what type of soil we have. So let's say that we have percentages of sand. The way that you use this is these are sideways. So like 90% would be, this is silt. So 90% silt, 80%, 70, 60, and so on. And then the clay is red sideways. So the clay would be red 90, 80, 70, 60. And then sand is red this direction. So this is 10, 20, 30. And they all should equal 100%. So you can't have more than 100%. So if we have loam soil, we have 40% silt. So this is 40% silt. We have 40% sand. So here's 40% sand, and then we have 20% clay. So clay is red across this way. So this equals 100%. And we also know that we have loam soil. So we'll be determining, you guys will be determining what type of soil was in the bucket based on the percentage of sand, silt, and clay. And so here we look at how things are permeable. So we've got a measure of time. So you guys did this with the filter. So sand, silt, and clay, you can see if we fill up the same amount with sand, silt, or clay, clay is obviously going to take a very long time. Sand is fastest. So sand is the biggest particle, clay is the smallest. And so the pore sizes, the sizes between each particle, are smaller with clay. And so the water has a harder time moving through. That's why here in Redding we have a lot of clay soil, and so it takes a really long time for the water to seep through. So that's why when it rains, it could not, like right now it's really dry outside, and when it rains, which it's supposed to on Saturday, it's the water pools up really fast, so it doesn't flow down very easily, and that's because we have a lot of clay, and so it takes a while for the water to seep down. If we get heavy rain, it can be flooding real fast, even if it's super dry. And that's because the pore sizes are small. All right, so some other things that we look at with soil, the cation exchange capacity. So this has to do with the amount of clay. So how does it absorb and release cations, which is important for plants. And so if you have clay, it's good because it holds a lot of nutrients. But the downside to it is that it does hold a lot of water, and so it doesn't release water very quickly. It's got very small pores, so it takes a while for the water to seep in, but then it holds on to water for a while, and so everything can become very waterlogged, which isn't a good thing. So you have to have a healthy mix of sand, silt, and clay in order to have good soil. And then base saturation, we look at different nutrients, so calcium, magnesium, potassium, sodium, and we look at that compared to aluminum and hydrogen. We look at that as a percent to figure out how good the soil is as far as nutrients go for the organisms. So acids are detrimental, bases are essential. Oftentimes you'll see that lime is added to soil, and that's to help it become more basic, to kind of neutralize the acids in the soil. All right, so other things we look at are what is in the soil. So microorganisms are really important in the soil. So things that we could have in there are fungi, bacteria, protozoans. Those are all pretty important. So they all serve a purpose, mostly breaking down nutrients into something that is usable by the plants. So it's pretty amazing. They account for about 80 to 90% of the soil organisms are all of these things that function to serve a purpose. So people that are dumping a lot of pesticides, herbicides onto the soil, it's pretty detrimental. So it's important to have those things. So dumping all that stuff onto the soil kills those things as well. And it might temporarily make your soil or grass or lawn appear healthy. But in reality, now you're going to have to dump a bunch of fertilizer on it because now you've made it nutrient poor. So those things are very important, and it's important to find a good balance and not use heavily or rely heavily on pesticides, herbicides, or fertilizer. All right, so let me move my little picture here. It's in the way. All right, so if we look at minerals, the rocks and minerals, they're finite, meaning that there's not unlimited amount of those things. So it's important to preserve them and to understand how they work and not to overuse them. So some are very abundant, some are very rare. And we've got a few terms here. So crustal abundance is how much concentration of an element is in the Earth's crust overall throughout the entire Earth. An ore is something that's mined for a profit. A metal is something that we can use to conduct electricity or heat, like aluminum, zinc, that kind of stuff. And then a reserve is where is it found in a large quantity. All right. So here we can see the abundance on Earth. So the Earth, you can tell just glancing at this right away, is that oxygen and silicon make up the more abundant. They're more abundant than anything else. So they make up the majority of the soil of the crust. So oxygen and silicon, which makes up a rock type called silicates, a mineral type called silicates. So they are very abundant, and then you can see things dwindle from there. But these are the majority of elements that we find in the Earth's crust. That's important. All right, and then we can see how many years left we have of these reserves. So aluminum, global reserves, 330 years if we use at the same rate. In the US, we have 2. And then you can see going down the list. Some things are not very abundant, and they're not found worldwide everywhere. So in some places they're very abundant, in some places they're not. But you can see this is finite. So the fact that we have just not, I mean, this is within our lifetime, all of these things except for the aluminum, all within our lifetime if we continue to use. So it's important to recycle, and it's important not to overuse these items. All right, so mining. So how do we get this stuff out of the ground? So there's a variety of different ways that we mine. So there's strip mining, open pit, mountaintop removal, placer mining. We'll talk about all of those. So strip mining is taking pieces of land. So you can see in this picture. It's also an open pit mine. So strip mining, removing strips of soil or rock to expose the ore. And then this happens to also be an open pit mine. So open pit just means that you can see it and it's not underground. So this is pretty often, it's the easiest to do rather than going underground. But it needs to be close to the surface. So there's a reason that we do it. And this would be that the ore is found either at the surface or near the surface. It might be deep underground, but it starts at the surface. So we would use surface mining. And then we've got tailing. So every time that we mine, no matter what kind of mining we do, we have product that we don't use. So it's not going to be just the ore that we find. It'll have dirt, rocks, other things mixed with it. And so those are called tailings. And so we have to put the tailings somewhere. And you can see in this picture they've dumped the tailings in this area. And so sometimes we can use that for cement. So sometimes you'll see that in some areas, cement will be different colored in the Midwest versus the West. And that has to do with what kind of aggregate, what kind of rock is there. So if there's a reddish type of rock, then more than likely the cement and building materials are going to take on a reddish tone. If it's not, then it'll take on a grayish tone or something like that. So really, we do use this material. We just use it for other things, mainly cement or building, sometimes gravel, things like that. All right, and then we've got mountaintop removal. So you can kind of see a little bit of this as you drive to Shasta. As you drive by the tennis courts, you can see a little bit of mountaintop removal, and that would be where Iron Mountain Mine is. So we've gone underground and also above. And then out towards Bridge Bay, you can see a little bit of mountaintop removal where we've got a quarry. And so, I mean, it's pretty much self-explanatory, removing the mountaintop. But we can remove it with explosives, tractors, whatever. But it's just taking parts of the mountain off, and that's because there's some type of ore that we are extracting. All right, and then placer mining. Placer mining involves rivers. So we're looking at minerals, metals, whatever it might be in there. And so we're digging through river sediment. So it's called placer mining because they're placer deposits. That's where the name placer, like the road, got its name, is there's a lot of mining in this area. And so it was used as that name. But placer mining, it's a typical sorting through a river, looking for gold around here. So that would be placer mining. And then subsurface would be our typical, like when you think of a mine, you think of like a mine shaft and going underground. So that's subsurface mining. So this would be, there's an ore that's deep. And so it wouldn't be beneficial to dig from the top down because you're just wasting time or wasting resources. So you would go down to the source. So around here, we have this type of mining as well. And so, it used to be mining for gold. We don't have a lot of this kind of mining anymore here. We do in the Midwest a lot, and that's in the East because of coal. But around here, we don't have a lot of this anymore, mainly because around this area, we were looking for gold. And so we don't do a lot of that anymore around here. But things that we can look for using this coal, diamonds, gold, those are some examples of things that we use. All right, and so we can see in this picture here, this table, that it shows surface mining and subsurface mining, and then some effects that it has on the environment. So this table is pretty important. I would definitely know this table. So when we talk about environmental science, we're talking about the effects that things have on it. So you have to know like the types of mining, but you also need to know the effects, the environmental effects, because that's what this class is all about. So effects on the air. So surface mining, there's dust, earth moving equipment. On the water, there's contamination, and that's for both. But contamination percolates through the tailings as water seeps through, goes into rivers and lakes and things from the tailings. And then for the soil, there's most soils removed. It could be replaced and with reclamation. So reclamation is just bringing it back to its normal state so that it's not ruining the land. Iron Mountain is a good example of that. We are reclaiming that. It's no longer used. It's actually a Superfund site, so it's a huge environmental problem. And so there's a lot of effort in it going to fix it and not have that go into Keswick. And then biodiversity. So there's habitat alteration, destruction, obviously for both, that it could affect organisms around. And then for humans, there's minimum for surface mining, but it could be affecting air quality. It could be affecting rivers, water quality. And then for the subsurface mining, there's minimal dust. So atmospheric wise, it's not too devastating, but there is a lot of acid mine drainage. So that's the big issue with Iron Mountain. Effects on the soil, not so much because it's subsurface. Biodiversity, same thing. It's not too bad. I mean, maybe the roads and things that are going to it. And then, of course, for humans, subsurface mining is pretty dangerous. And so we do see mining problems with that. And that's it. So I will see you guys next time.